Let's take a look at section 7.2, which is integrating functions all with trig integrals. We've looked at functions that have had some trigonometric terms, usually sine and cosine, but even all the other four as well, back when we did substitution and even when we did some of the integration by parts problems. The thing about the problems in this section is we're going to have higher powers of those trigonometric functions that make it a little bit more different than what we've encountered up to this point. The first thing I'll go ahead and say here, and it's probably the most important thing for you to remember throughout the problems in this section, this very first thing, when you have trig functions within integrals, the way that you're going to know which one to break down and try to rewrite is you're always going to look for odd powers of sine, cosine, tangent, and cotangent. So if I have a sine cubed, I know that's what I will attack inside the integral. If I have a cosine to the fifth, I'll work with that. If I have a tangent to the seventh, you bet, I'll work with that. Same thing with cotangent to any odd power. That's what you should work with inside the integral. We'll talk about how to work with them on down here. Now, the functions, the trig functions that you want even powers of are the secant and cosecant. So if I have a secant squared, a secant to the fourth, a secant to the sixth, that's what I will attack in the problem. Same thing with the cosecant. What if I have an odd power of secant in a problem? I would avoid that and try to work with the other trig function. Now, when I was saying that you want to attack or work with odd powers of sine, cosine, tangent, and cotangent, here's how you do that. Let's say, for example, you have a sine to the fifth power inside of an integral. Well, what you're going to do every single solitary time is you're going to take all but one power of that odd power and rewrite it in terms of cosine. So when I can say, well, sine to the fifth is the same thing as sine to the fourth times sine squared. Well, sine to the fourth is the same thing as sine squared quantity squared. Sine squared could be rewritten as 1 minus cosine squared using your Pythagorean identity. So you can say, well, this is sine squared squared, still gives me back my sine to the fourth. Now, how is this far better format than what you started with originally? I don't know how to integrate the sine to the fifth power. However, I do know how to integrate this. It's a really easy substitution problem because all I would need to say is, let's let u equal the cosine of x, and then the derivative of cosine of x is going to be the negative sine of x dx. I can easily multiply by a factor of -1 inside and outside the integral to enable that to occur. Now, similarly, if I have a cosine to an odd power, and I'm just using the fifth power as an example here, it could be the seventh, the ninth, the 11th, whatever, and you will always take all but one power of it and rewrite it as another trig function. So if I have cosine to the fifth, I know it's cosine to the fourth times cosine. How do I write cosine to the fourth in terms of sine? I know that 1 minus sine squared is cosine squared, so cosine to the fourth is 1 minus sine squared quantity squared. And then once I do that, this problem would be set up for substitution within the integral because I could say, let's let u equal the sine of x. And we know that the du would be the cosine of x dx. It would work out beautifully. Now, if I have the tangent function, same idea. If it's odd power, sine, cosine, tangent, and cotangent, I treat it the same way every single time. I'll take all but one power of the tangent function and write it in terms of secant squared. Well, keep in mind your Pythagorean identity for tangent, and you can go back and look at your Pythagorean trigonometric identities if you need, but tangent squared is equal to secant squared x minus 1. So I can say, well, since tangent squared x is secant squared x minus 1, tangent to the fourth is secant squared x minus 1 quantity squared, and then I could have my remaining tangent left over. Now, what I would do with this is I would then say, well, I could let u equal the secant of x, and the derivative of u would have to be secant x tangent x. So I would hope that there would be another factor of secant x to go along with that tangent x for the derivative. So we'll have to see that in some problems. For the next one, similarly with the cotangent, What if you have an odd power of cotangent? You'll break all but one power down into another trig function. The trig function in this case is we're using the Pythagorean identity that cotangent squared is equal to cosecant squared x minus 1. So I can say, well, all right, if cotangent squared is cosecant squared x minus 1, then this squared is going to give me cotangent to the fourth times the cotangent of x. That gives me back my original. But now this is set up to where substitution is going to work nicely, and I'll let u equal the cosecant function in there. And I promise these problems are going to work out very nicely if you do that. Now, on the other hand, I said you look for even powers of secant and cosecant. So if I have, say, a secant to the fourth, what am I going to do? I'll break all but two powers down, and I can say, well, secant to the fourth, you know, that's secant squared times secant squared. What I want to do with this first secant squared, I want to leave one of the secant squareds. I'll call this secant squared what it's equal to in terms of tangent. Well, it's 1 plus tangent squared. So this takes the place of the first secant squared. I leave my second one in there. Why would I do that? Because now if I let u equal the tangent of x, du is going to be secant squared x dx. It's going to work beautifully. The only ones that you need to work with a little bit are the tangent and cotangent, because the derivative's not exactly in there, but the other four works nicely. The cotangent to the fourth, you break all but two powers down, and so you say, well, if it's to the fourth, then you just say cosecant squared times cosecant squared. One of the cosecant squareds you need to write in terms of cotangent. As we discussed earlier, cotangent squared is equal to cosecant squared minus 1. So cosecant squared is equal to 1 plus cotangent squared. Okay, now what happens when I do this? I would let u equal the cotangent of x, and then du is going to be the negative of the cosecant squared x with respect to x, which I could easily get that in there by just multiplying the inside and outside by a negative. Okay, now let's look at some examples of problems in this section. For the first one here, I want to look at the integral of sine to the fifth cosine squared with respect to x. Automatically in this problem, you should know instantly what you're supposed to do in this problem. You see a trig function with or I should say you see a sine function to an odd power. You always attack odd powers of sine, cosine, tangent, and cotangent. So I can say, well, I'll attack that odd power. When I say attack it, well, just like I had back on the notes page before, sine to the fifth is sine to the fourth times sine. That sine to the fourth can be rewritten as sine squared squared. We know that sine squared, same thing as 1 minus cosine squared. And so I can say it's 1 minus cosine squared, quantity squared, times the sine of x. I went ahead and squared that out here. 1 minus cosine squared is equal to, when I square that group, 1 minus 2 cosine squared x plus cosine to the fourth x. I still have my sine function in there. So please notice I went back into my problem and I said, well, I know I have the cosine squared in there. I'm not messing with it yet. This sine to the fifth, I'm choosing to rewrite in equivalent format. It's equal to 1 minus 2 cosine squared x plus cosine to the fourth x. I get my whole functions in terms of cosine first. Now, times the remaining sine of x dx. At this point, I could then say, well, you could distribute that cosine squared through this group to get this function in terms of cosine. And now I can say, well, if I let u equal the cosine of x, since that's all the terms inside this three-term function here, then du would have to be the negative of the sine of x dx. I could easily multiply by a negative 1 on the inside. If I multiply by a negative on the outside, that's what I did right here. And then the negative sine x dx becomes du. And then this function is just going to become u squared minus 2u to the fourth plus u to the sixth. That's right there. At that point, you know it's just power rule. So I get the negative of the group, u cubed over 3, minus 2u to the fifth over 5 plus u to the seventh over 7. And then I can say, okay, I know that u is just the cosine, so then we substitute back in our answer. We'll get negative 1/3 cosine cubed x plus 2/5 cosine to the 5th x, and then it would be minus 1/7 cosine to the 7th x plus your constant of integration. Okay, now you're thinking, that wasn't too bad. Not at all. And again, please remember in these problems, whenever you're given two trig functions, you should instantly know the one that's ideal to work with, because it's going to be the one to the odd power if it's sine, cosine, tangent, or cotangent. So when I look at this one, I don't want to work with that sine to the 4th power. An even power, I'd have to use the power reduction formula. That's best stayed away from. So here, I'm going to work with the cosine cubed, and I can say, well, cosine cubed is just cosine squared times cosine. Cosine squared is 1 minus sine squared times the cosine. So now I go back into my problem. I have the integral of sine to the 4th. All of this is the cosine cubed, but I rewrite all but one power of the cosine in terms of the sine, namely calling it 1 minus sine squared. At that point, just like I did with the cosine function in the last problem, you could distribute through and say, well, this is going to become sine to the 4th minus sine to the 6th, and then I'll have my cosine of x dx. At that point, I let u equal the sine of x, and then du, derivative of sine is cosine x with respect to x. So all of this just becomes du in my problem. This is just going to become u to the 4th minus u to the 6th. At that point, it's a very nice power rule where you say, well, the integral of u to the 4th minus u to the 6th is u to the 5th over 5 minus u to the 7th over 7 plus your constant of integration. Then at that point, you can say, well, all right, u is the sine of x, so we're going to get 1/5 sine to the 5th of x minus 1/7 sine to the 7th x plus that glorious constant of integration. Now, I've been saying that you want to look for odd powers of sine, cosine, tangent, and cotangent. That's not always going to happen. So what if you have a problem where you don't have odd powers of it? Let's talk about that. That's where I'm doing number 3. This is ideally not the scenario you want to fall in, but sometimes you're going to. So what if I have an even power of sine? I have the sine to the 4th power of x with respect to x. I don't have an integration formula for that. So what I want you to do is I want you to remember, well, we can always at least call sine to the 4th sine squared squared. Now, from your trigonometry days, you might remember the power reduction formula. The power reduction formula for the sine function is, usually in that class, we called it a fraction. We said 1 minus the cosine of double the angle over 2. It was called the double angle formula sometimes as well. So sine squared x is going to equal 1 minus the cosine of 2x all over 2. So you always double whatever that angle is and divide by 2, and that's equal to the sine squared. I prefer, instead of putting a fraction all over 2, I prefer the 1/2 out in front. So I always say 1/2 times the group, 1 minus the cosine of twice the angle, is equivalent to that sine squared function. So please remember, sine squared is 1/2 times the group, 1 minus the cosine of twice the angle. So the inside is sine squared, but I had sine to the 4th, so I have to square that group. No problem. Especially when it's a product like this, I can say, well, then that 1/2 is going to become 1/2 times 1/2, which is 1/4. And then I need to square out this binomial. When you say 1 minus cosine 2x times 1 minus cosine 2x, you get 1 minus 2 cosine 2x. And then your last term is going to be cosine 2x times cosine 2x cosine squared 2x. So the problem here is you use the power reduction formula, but you still have a power on a trig function after you've done it. Okay. So now I use the power reduction formula on that cosine squared 2x in here. Your power reduction formula for the cosine function, it's extremely similar to the sine function. The sine function, it's 1/2 times 1 minus the cosine of twice the angle. The power reduction for the cosine is 1/2 times the group 1 plus the cosine of twice the angle. That's the only difference, is the sine of the cosine function, but it's a cosine in both of them. So Cosine squared 2x is going to be 1/2 times the group 1 plus the cosine of double that angle, now 4x. So I can then say, well, all right, then sine to the 4th power of x is going to be 1/4 times the group 1 minus 2 cosine 2x, and then I would have 1/2 times this group, so I get plus 1/2 plus 1/2 cosine of 4x. Now what I've done when I went down here is I said, well, all right, then my original problem is equal to this 1/4. I can just factor to the outside. I said 1 plus 1/2 is 3/2, and sorry it got a little sloppy here, minus 2 cosine 2x plus 1/2 cosine 4x. I'm integrating all of that with respect to x. Okay, so when I do that, my 1/4 stays out as the coefficient in front. Integrate the first term with respect to x. 3/2 integrates to 3/2x. The second term, it's a negative cosine. The integral of negative cosine is a negative sign, but when you integrate it, you need to divide by the derivative of the angle. Dividing by 2 gets rid of that 2 out front, and you just have minus the sine of 2x. Now the last one, and I accidentally put a cosine, so I had to white it out and put a sine, and it didn't show up very well. But the integral of cosine, and it's a positive cosine, would be a positive sine. And I also have to remember, well, I would divide by the derivative of that angle, which I'm dividing by 4. So 1/2 becomes 1/8 sine of 4x plus your constant of integration. Then I just cleaned up that answer by distributing the 1/4. I got 3/8x minus 1/4 the sine of 2x plus 1/32 the sine of 4x plus the constant of integration. Okay, next page here. If I do a definite integral of a function like this, and this time I'm doing sine cubed times cosine to the 1/2 power, automatically you know to work with the sine function because the sine function is to an odd power. So instantly I would look at that sine cubed x and say, well, I'm going to call that sine squared times sine x, and the sine squared is going to be rewritten as 1 minus cosine squared x. So I have 1 minus cosine squared x times cosine x to the 1/2 power times the remaining factor of sine x that I didn't account for right here, sine x, with respect to x. Don't have to change my limits of integration now because everything is still in terms of x. But now I'll remedy that. I can say, well, I do want to use substitution at this point. If I let u equal the cosine of x, and then I can say, well, du is going to be the negative sine of x dx. I'd have to multiply by a negative on the inside in order to call this du, which means I also have to multiply by a negative on the outside. You'll see I multiplied by a negative on the outside. The negative sine x dx became du. And then my group, I would have this cosine to the 1/2 distributed through this group. The cosine to the 1/2 becomes u to the 1/2. The cosine squared times cosine to the 1/2, that'd be cosine to the 5/2 power. That becomes u to the 5/2 power. And of course, we're still subtracting it. So now, I also changed my limits of integration. I didn't show that up here, but you know that's pretty easy. You just say, well, the lower limit, it'd be the cosine of 0. Cosine of 0 is 1. Your upper limit, it would be the cosine of pi/2. Cosine pi/2 is 0. So now we have the negative integral from 1 to 0 of this function in terms of u. Power rule on both terms. The first term becomes u to the 3/2. And then you'll be multiplying that by the reciprocal, 2/3. The second term becomes u to the 7/2, and you'll multiply it by the reciprocal, 2/7. We're then evaluating, please notice what I've done here. Instead of evaluating from 1 to 0 and then remembering to change the sign, I just said, let's flip those limits of integration and it will get rid of that negative sign. So I'm evaluating from 0 to 1 over here and not having to worry about the negative out front. When you plug in the 1, you'll just get 2/3 minus 2/7. We know that's going to give us a common denominator of 21. We'd have 14/21 minus 6/21 for 8/21. And then the lower limit of integration is just 0, so it would give us a 0. 8/21, final answer. The ones I've been looking at thus far have just been dealing with the sine and the cosine functions. You'll have some problems in your assignment that will have integrals with tangent and secant. Please remember, this is just a recap of what I talked about earlier. You look for odd powers of the tangent function, and you're going to rewrite all but one power in terms of the secant function and use the substitution of u equals the secant of x. You look for even powers of the secant function, and you're going to rewrite all but one term of the secant squared x as a tangent function. Let's see those in action. For number 5 here, I'm giving you the integral of tangent cubed secant to the 7th dx. So I instantly say, ooh, tangent is odd. That's what I'll work with. So I say I'm going to work with that tangent cubed x. I'll call it tangent squared x times tangent x. Tangent squared x is the same thing as secant squared x minus 1. So now I can go back into my problem and say tangent cubed is going to be written as tangent squared times tangent. This tangent squared put in terms of secant. Secant squared x minus 1 is equivalent to tangent squared. Now I can say let's put that out in front along with the other secant term in the problem, the secant to the 7th, times the remaining factor of tangent x dx. Why do we want to do that? And why didn't I go ahead and distribute that secant to the 7th through that group? That'd be a big mistake. Please notice, here's why. When you do substitution, the substitution you want to make in this problem is to let u equal the secant of x. Remember from Calc 1, the derivative of the secant of x is secant x tangent x with respect to x. So you'd say, well, I need a secant and a tangent in that derivative. I have it. Right here's a secant, right here's a tangent. I only need one power of that secant along with that tangent and the dx to become du. So please notice what I've done here. I've said one power of that secant and that tangent and the dx becomes du. I'm going to have 6 powers of that secant left over. That's where the u to the 6th came from there. And then I can say, well, then this group is going to be u to the 2nd minus 1. Now I distribute the u to the 6th throughout that group, and I get the integral of u to the 8th minus u to the 6th integrated with respect to u. First term would become u to the 9th over 9. Second term, u to the 7th over 7. I went ahead and put it back in terms of x. We'll get 1/9 secant to the 9th of x minus 1/7 secant to the 7th of x plus your constant of integration. So you're thinking, hey, this stuff isn't bad. No, it's really not. It's quite fun, actually. Now, instantly in this problem, in each of these problems, you should know what to attack before you even start working the problem. As soon as I look at this and say, oh, I've got an even power of the secant function, that's what I will attack. How do I attack it? I rewrite all but 2 powers of it as another type of function. So what I mean here, I know secant to the 6th, same thing as secant to the 4th times secant squared. How do I rewrite secant to the 4th? It's secant squared squared, where secant squared is written as 1 plus tangent squared. So now I have, for that secant to the 4th, 1 plus tangent squared quantity squared. I went ahead and squared out that group. 1 plus 2 tangent squared x plus tangent to the 4th x times the remaining secant squared x that I had on the outside. Now I go back into my problem and I can say, well, we're going to have this square root of the tangent function, which is tangent to the 1/2 power, and it's going to be multiplied throughout this 3-term function here. When I multiply it into the first term, it gives me tangent to the 1/2 power. When I multiply it into the second part, it's going to give me 2 tangent to the 5/2 power. And into the third, it's going to give me tangent to the 4.5, or I should say 9/2 power of x. So this right here is just taking this, multiplying by the square root of tangent to get to that. Now, I have my remaining secant squared that I've had since the beginning still left there with a dx. So now I can say the whole reason for leaving that secant squared out there like that is I'm going to do a u substitution. Let's let u equal the tangent of x. Du is going to be secant squared x dx. So I know that that du is going to take the place of the secant squared x dx. I can rewrite this as u to the 1/2 plus 2u to the 5/2 plus u to the 9/2. I also have to change the limits of integration if I'm going to put this in terms of u. I've done that right here. You're evaluating the lower limit in your function for u. It's that, well, it's the tangent of 0. Tangent of 0 is 0. Your other one is the tangent of pi/4. You know what pi/4, your sine and cosine are both the square root of 2/2. Thus, the tangent, that's the ratio of the sine over the cosine, is just 1 at that angle. So I can say I'm now integrating from 0 to 1 instead of 0 to pi/4 of this function. I use the power rule on each of the terms. I get to 2/3 u to the 3/2. That second term would become plus 2u to the 7/2 times 2/7. That's where you see the 4/7 u to the 7/2. And my last one becomes u to the 11/2 times 2/11. That's where that came from. And sorry, this is sloppy. This is much sloppier than how I normally am. I think the pen I was using was not very good. So whenever I'm trying to evaluate this now, I know that the only limit of integration I need to worry about is the upper one, because when I plug a 0 into that function, I'll get a 0. When I plug in the 1, I'll just get 2/3 plus 4/7 plus 2/11. I went ahead and got a common denominator of 231 there. And then when you add all those up, it'll get you 328/231. And we would want an exact fractional answer, no wimpy decimals accepted in these problems. For another one here, let's say I throw in one with a cotangent and a cosecant. Instantly, as soon as you look at this problem, you should know what you should do. Please remember, back on the very first page, I said you look for odd powers of sine, cosine, tangent, and cotangent. Well, I've got an odd power of cotangent. No question. I'll break up the cotangent to the 5th power. How do I do that? Break it up as cotangent to the 4th times cotangent to the 1st. Cotangent to the 4th can be cotangent squared, quantity squared. Well, cotangent squared is equal to cosecant squared x minus 1. Now, when I square out that group, I would get cosecant to the 4th minus 2 cosecant squared plus 1 times the remaining cotangent. Now I bring this back to my problem, and I can say that cotangent to the 5th is being replaced with all of that and a factor of cotangent. I'm sticking that cosecant down. I didn't do anything with it. And I'm integrating this with respect to x. At this point, the whole reason for rewriting it in terms of cosecant is now I'm going to let u equal the cosecant of x. Well, the derivative of the cosecant of x is negative cosecant x cotangent x dx. Ooh, I needed my dx there. Bad on me. Let me put that dx. That's bad. That bugs me. So then I can say, ooh, better pen too. Then I can say, at this point in the problem, I'm ready to do my integration. All I would have to do is multiply the inside by a negative, multiply the outside by a negative. That's why you see the negative right here. Now, one of those powers of cosecant is going to go along with the cotangent and the dx and the negative to become the du. That's where that comes from. Well, there's 4 other powers of that cosecant left in there. So I went ahead and did that, and I said, well, if I multiply this group by the remaining 4 powers of the cosecant to the 4th x, I would get cosecant to the 8th minus 2 cosecant to the 6th plus cosecant to the 4th. In terms of u, I get u to the 8th minus 2u to the 6th plus u to the 4th. At that point, it's easy to integrate just by your power rule. You say negative 1/9 cosecant to the 9th. Notice I'm going ahead and putting it back in terms of x. Your second term would be, well, before you distribute the negative, the second term would be negative 2u to the 7th over 7. Distributing the negative makes it positive 2/7 cosecant to the 7th x. My last term would be u to the 5th over 5. This is going to make it negative. And ooh, I need the negative sign out in front of that, minus 1/5, ooh, ugly, minus 1/5 the cosecant to the 5th of x plus your glorious constant of integration there. Last page here. So a couple other things I wanted to show is what if we have something that doesn't really fit any of the scenarios? Like if I have the integral of tangent over secant squared integrated with respect to x. Typically what we do in problems like this is to go ahead and try to put everything in terms of sines and cosines. So what I did here, exactly that. I said, well, the tangent of x is sine x over cosine x. I know I'm dividing by secant squared x. Secant squared x is the reciprocal of cosine squared x. So when I divide by secant squared, that's the same thing as multiplying by cosine squared. Now, that makes it really nice because I can say one of those cosines cancels with this cosine, and I would just be left with sine x times cosine x dx. At that point, you really can't go wrong. You can choose either of those functions for your substitution. The slightly easier choice is to let u equal the sine of x, and then du is the cosine of x dx. And so you can say, well, hey, this is just the integral of u du, which is going to be 1/2 u squared plus c. I can say, well, this answer then is 1/2 sine squared x plus c. Now, I wanted to show you another technique here, and I'll pass on the showing you graphically. I'll talk about that in a second. The other option here is the integral of tangent x over secant squared x dx. I can say, okay, similar to what I did before, actually this time, let's not convert it to sines and cosines. I started to say, what if I would have this same thing and let u equal the cosine of x, and then du would be the negative sine of x dx. We'd get this same answer I'm getting this way. So whether I did the substitution with letting u equal the cosine and du being the negative sine of x dx, you're going to get the answer I got right here with not converting it. So let's say I didn't convert, and instead I let u equal what's inside of a group to a power. Well, u is the secant of x. This is an important technique to show you here, guys. We haven't done any problems where it required, I'll say, some creative thought. Here's what I mean here. Whenever you do your du, you say, I do not have a factor of secant x tangent x dx in there. So at first you might think, well, I can't do this substitution. You most certainly can. Now, while you can't multiply by a variable term of x on the inside and the outside, you can't do that. You can always multiply the inside by a constant if you divide by the constant on the outside. As long as you keep that term inside, it's okay. So here's what I mean. When I see that I need a du of secant x tangent x dx, and I have a tangent x dx, but I don't have a factor of secant x up there with it, let's put it up there. So what am I doing from this step to this step? I'm multiplying the numerator by secant x. I'm multiplying the denominator by secant x. That's a legitimate maneuver. I'm multiplying by an understood 1. Now, here's how that helps. It helps because that denominator, that's still just going to be u to the 3rd power down there. That numerator, secant x tangent x dx, all becomes du. So I can say, well, this is going to simplify after my substitution to the integral of 1 over u cubed du. That's the same thing as u to the negative 3. So when I integrate that, it becomes u to the negative 2 over negative 2 plus the constant of integration. U to the negative 2 over negative 2 is the same thing as negative 1/2 times 1 over u squared, which would be 1 over secant squared plus c. And then you can say, well, 1 over secant squared, that's the same thing as cosine squared. So why not call that negative 1/2 cosine squared x plus c? Gorgeous. Now, you look at these two and you think, well, wait a minute, those two are not the same answer. One of them's wrong, or isn't it? Absolutely not. They're both correct answers. It's just that whenever you're integrating, the answer that you get, it's just saying that function has a derivative of this, meaning this function and this function must have the same shape. They don't have to have the same y values. Now, let me go ahead and show that in here. I wasn't thinking I was going to, but I want to. If I'm looking at this function here, the first answer, 1/2 sine squared x, so I'll say fraction 1/2, and then sine squared x, I'll do as the group of the sine of x, close the angle, close the sine, and square the function. Whoa, wait a second, John. I'll get it right in a second, guys. Delete that off. Delete, please. There we go. Sine squared x. Now, for the y2, I have my negative 1/2 cosine squared x, so negative 1/2. And then I'll have the group cosine of x, close the angle, close the cosine, and I want to square that. Okay? And it doesn't really matter whether you write your fraction like the first one I did or the second one with the 1/2. Doesn't matter. It's the same thing. Now, I do want to make sure I'm in radian mode. You always need to be in radian mode anytime you're graphing, so that's good. Now, I want to see these two functions. Let's say I do the zoom trig screen. This one may not be the greatest, but it's a good starting point. Zoom 7. This first function coming in, that's my negative 1/2, the sine function. Yeah, this is actually a pretty good screen. Gorgeousness, oh gorgeousness. And you say, why is that so gorgeous? All I'm trying to show you is that these two functions have the exact same shape. Doesn't mean that they're the exact same function. They're not. But the shape of the 1/2 sine squared x and the shape of the negative 1/2 cosine squared x, identical. So since they have the identical shape, they have the identical derivative. So if we took the derivative of this and the derivative of this, either way, it's going to lead back to that function. Great problem. Now, some problems in this section might require you to do the product to sum formula. Anytime that that's the case, you would be given that within the problem. Such as right here, if I say, guys, in this problem, please use the trigonometric identity. The sine of mx times the cosine of nx is equal to 1/2 times the sine of m minus n times x plus the sine of m plus n times x. So it took a product of a sine and a cosine and turned it into a sum of two sine functions. That's wonderful because it's easy to integrate these two sine functions after you've done that. Let's see that down here. So if I have the sine of 4x times the cosine of 5x integrated with respect to x, I just say, well, all right, this 1/2 I can bring out in front of my integral and then say it's the integral of the sine of the difference of the angles. 4x minus 5x would be negative x plus the sine of the, sum of the angles, 4x plus 5x for 9x. And then each of these are extremely easy to integrate. You say, well, how do I integrate the sine of negative x? I can say, well, I know that the integral of positive sine is a negative cosine, but then it would be the negative cosine of negative x divided by the derivative of that angle. Well, dividing by -1 makes that negative cosine a positive cosine again. So that's why I got that positive sign there. Now your second term, you say, well, yet again, when you integrate the sine function, you get the negative cosine of that angle divided by the derivative of that angle. Well, you're going to get the negative cosine of 9x divided by 9, or 1/9 the cosine of 9x, plus your constant of integration. All I've done beyond that, I just left the 1/2 out in front. And then you wouldn't have to do this, but what I'm showing here is your cosine. Since it's an even function, does it matter if you have a negative angle in there? No, the cosine of negative x is the same thing as cosine of x. Keep in mind that's you could remind yourself of that, because if you think cosine of pi over 4 we know is the square root of 2 over 2, well, the cosine of negative pi over 4 is also a square root of 2 over 2. Doesn't matter the sine of the angle, it's the same thing. So I just went ahead and said, the cosine of negative x, same thing as the cosine of positive x, and then minus 1/9 the cosine of 9x plus your constant integration. That should do it for this section. Please do try the problems on Achieve in this section. I think you'll have some fun memories of trig as you do these problems and stuff. This is a good section, but it pales in comparison with the beauty of sum coming up here. Oh, good stuff.